We got a lot to cover today, and it's basically 9:30. So the next couple classes are going to involve some chemistry that I think is going to require some substantial practice, specifically with regards to stereochemistry. We're going to be showing examples of fairly complex reactions where there's going to be a lot more bond formation, bond reorganization than perhaps we've been used to. And within these reactions, there's going to be some stereochemistry, which will require you guys to think about some specific sort of transition state models, if you will, to get them to work. And the first one that we're going to talk about today is one that I think is one of the most probably important reactions, certainly one of the most important, powerful reactions in sort of synthetic organic chemistry and certainly modern total synthesis, in part because of the fact that it's become clear, but we're going to be making multiple carbon bonds. We're going to be having specific regioselectivity in these reactions that we'll see. We'll have specific stereochemistry that we'll see. And so you'll get a sense for what the complicating, as well as, I think, complexity building chemistry that's going to take place in here. Before I get into Diels-Alder's, we've talked a bit about molecular orbital theory to a certain extent more superficially. Maybe some of you took a class where it went into a little bit more depth. But for the most part, when we've talked about molecular orbital theory, we've simply talked to it in terms of, and talked about it in terms of the fact that when you're sort of making a bond, you're taking a couple electrons and putting them together, right? I think the most important thing is to recognize that when you're bringing a couple electrons, or when you're making a bond, right, whatever they might be, let's say, for example, it's going to change based upon what it is, but let's just imagine it's simple. People might, let's stick with carbon, because we're carbon, maybe a little bit different. But when you're in a symmetric system like this, each of those carbons to make a carbon-carbon bond, right, is going to bring an electron to the party, right? And so each of these electrons will sort of form a bond. That process is an energetically favorable process, right? So they end up pairing together. And in general, what we're talking about here, down here is, right, the sigma bond, right? That's the sort of bonding orbital. This is something that's obviously we've discussed, right, where you have, you'll occasionally see it drawn like this, right, where we'll have sort of a sigma bond, energetically favorable process, and then up here, right, you'll have a sigma star, which will be the sort of anti-bonding orbital, right, and that's almost the opposite, right, of sort of sigma bond. So this idea of molecular orbitals, there are bond-forming properties helping to explain favorable energetics. You've seen systems that look like that. Now, when we get to conjugated systems, when we start talking about pi system, it gets a little bit more complicated. And I'm not going to go into crazy degree of sort of quantum chemistry, and truthfully, I don't even necessarily understand that the sort of the extreme levels of this, or the sort of deeper levels of this. But if we start to think about a reaction of a conjugated system like 1,3-butadiene, right, and we're focused on the pi bonds, right, we have what amounts to 2 p orbitals, right? And each of those 2 p orbitals is bringing sort of 2 electrons, right, if you will, to the party, kind of like the sigma bond each brought 1, right? And then again, we have sort of 4 electrons. So we have 4 electron total system. So as you might imagine, in these systems, each of these is pi bond and sort of an anti-pi bond, but we really have 2. And it's not as simple as that. It turns out that they hybridize a little bit more, not too dissimilar to what we've seen in other cases. So there's a sort of hybridization in place, and the electrons are going to move around throughout that system, right? So the way to sort of think about these 4 different orbitals, right, is different sort of energy barriers sort of wave functions to sort of help us sort of understand that, but sorry, I'm running out of space up here. But again, as I mentioned, there's going to be sort of 4 orbitals. And each of those orbitals, we're going to add a couple electrons. Right, so I'm going to add 2 electrons to this one, and then we're going to add 2 electrons to this one, and this one will be empty, and this one will be empty as well, right? So fill as we would imagine from the ground up. Okay, so these are the sort of orbitals, but it turns out that, as I sort of stated, these, some math behind this, but it's sort of wave functions that each of these will be based upon, and what you could sort of think about, right, when you think about wave functions and when you think about waves, what do we think about in terms of the energetics of waves? Right, things that are higher frequency, you get more in a smaller, right, it's going up and down a lot more. Sort of lower energy systems are you know, bigger arcing, right? So when we think about energy and waves, right, the wider the waves, the lower the energy, the more that you have within there, the higher the energy, right? So this is something you guys are probably semi-comfortable thinking about, right? So within that, right, we can have a series of different amounts of what we would call nodes, right? So oftentimes people use the term node to refer to how many times we bisect that line, right? So on the first one, we would have 0 nodes, right? So the wave function would basically just be a curve, right? And so when you'll see people filling these, right, you'll usually shade one side all the same way, basically meaning that all of them have, right, a wave. The wave is all on the top side, for example, right? When we get to the second one, what's going to be the second highest? It's going to be a single node, right? And where we put this node, right, well, we can put it at various different places, but obviously I think the simplest place to put it would be in the middle. Right, so I basically shaded the part of that, yeah.
It's just like harmonic scales.
Yeah, right. So then on the, we'll be down here on this one, we'll have effectively 2 nodes. And then the last one would be all of them, right? Okay, so this is how we sort of fill these sort of molecular orbitals, and how we sort of think about the different energetics of them, right? So higher in energy, right? And what becomes important specifically in Diels-Alder chemistry and a lot of chemistry that we're going to learn about is what we sort of call the frontier molecular orbitals, right? So when we're thinking about, say, for example, this reacting as a nucleophile, right? If you were to think about which electrons would be the most likely to attack something, which one would you think would be the most nucleophilic of these orbitals? Which representation do you think would represent the most likely to behave in a nucleophilic way? Yeah. The lowest?
I'd say so. Because you see they're all lined up next to each other.
But they're in the lowest energy. Right? What's going to want to attack? Right? The higher energy, but there needs to be something there. Right? So it's what we would call the highest occupied molecular orbital. Abbreviated to HOMO, highest occupied molecular orbital. And so that's the orbital that's going to, it's the highest in energy where we have electrons. So the highest in energy electrons, right, are going to be the ones that are going to be doing the attacking. Right? Does that make sense? Right? The highest energy electrons are going to be the ones doing the attacking. Right? Meanwhile, if you were going to put electrons into this system, where would you put them? So from the converse side of that, if this diene was going to behave as an electrophile, right, which one would you attack? Rami? The lowest here? There's already electrons there, though. You can't put electrons where there's something. Right, if we dump electrons into a sigma, when we're making a sigma bond, what are we attacking? We're attacking a sigma star, right? That's usually the lowest unoccupied, right? So there's already electrons here, we can't put any new ones here. There's already electrons here, we can't put any new ones here. So you're right that it's the lowest in energy, but it's the lowest energy that's unoccupied. right? And so this is the lowest unoccupied molecular orbital, which we refer to as the LUMO. So when we're talking about chemistry, and specifically this will be important for Diels-Alder chemistry, when we're talking about reactivity, what we're generally going to be referring to is chemistry taking place between a nucleophile, which would be represented by the HOMO, and the electrophile, which would be represented, as you guys can imagine, by the LUMO, right? And so that should make sense. Right? Does that make sense? Right? So these are the molecular orbitals from lowest to highest, right? So this is the representation of the orbitals if they're behaving as a nucleophile. This is the representation of the orbitals if they're behaving as the electrophile. Got it? Okay. So a Diels-Alder reaction when we're talking about a Diels-Alder reaction, what we're referring to is a cycloaddition reaction between a diene and an alkene of some sort. So this is a classic sort of example of a Diels-Alder reaction, right? And what ends up happening is a lot of things get pushed at the same time. It's generally a concerted process where, let's see if I can get some colored chalk.
It has to be a cis like that?
What's that?
It has to be cis like that? Or
Yeah, so the diene, as we'll sort of get to, the diene will adopt an S, it's what we call S-cis, right? So it's not cis in terms of there's only one group on each side, so it's not cis as we know it, but it is actually called S-cis, which basically means that the diene, the two alkenes are on the same side. So, anyways. But yes, they need to sort of adopt that conformation. And so as you can sort of see, what you're generating is 6-membered ring, sort of pushing the electrons around there. And if you think about, right, our, right, okay. So anyway, so this is the Diels-Alder reaction. So why does this work? How does this work? Well, we've just discussed the molecular orbital of the diene. Let's discuss the molecular orbital of just acetylene, ethylene, right? Just a single double bond. Right? So if we have a single double bond using what we learned over here, how many different rows are we going to have? Right? Previously we had 4 because each double bond was sort of bringing a pi star and a pi bonding orbital. Right? In this case, we're only going to have the 2. We're going to have basically the pi bond and the pi star, right? So 2 orbitals. That's all we're going to have, right? And if we fill these up, right, what's the wave function of the bottom one going to look like? If we're going to shade those nodes, are we going to shade them on the same side or are we going to shade them on opposite sides? The same side, right? Because that sort of wave function idea, right? Lowest in energy isn't going to have any nodes. And the only other possibility is one node, which would look something like that, right? So of these 2, right, we've only got 2 electrons in the system, so we're going to fill those up. The bottom one we would refer to as the HOMO. And the top one is going to be the sort of LUMO, okay? All right, so in this reaction, right, as you can imagine, right, just thinking about sort of electrophile, nucleophile chemistry that we're comfortable with, one of these is going to be the nucleophile, and one of them is going to be the electrophile. It could be one way or another, okay? So I'm going to erase this over here, just to make some space. And what I'm going to do right? So what's going to happen, right, is we can have two different types of reactions here. Either this could become our nucleophile, right, in which case it's going to react with our electrophile. So either this is going to react with this, right, or this is going to be our nucleophile and this is going to be our electrophile, right, and these could react together. All right, so let's take a look at what that sort of means. Right, let's go ahead and let's draw the first one, right, where this will be our nucleophile. And this is the first one that I'll show this will be the nucleophile, this will be the electrophile. And this is what we call sort of normal electron command Diels-Alder. It turns out that both of them will work, as you can imagine, as I'll show you, but in general, the early Diels-Alder reactions that were learned, basically the diene was the nucleophile. If we draw that in that form, right, we're going to shade this side. We're going to shade this side. And what you'll see, right, is if now we're going to be over here, depending on which way we put it. See how that phase matches? And that phase also matches. You guys see that? So basically, or if you want to say the bottom, so basically, you're going to get, let me just do the color here. Or if we want to think about it from a wave function standpoint, right? Oh, God. Oh, this is not. Right, so if we'd imagine this as a continuous wave, right, the node would be here, and it would go down, and then it would stay down here. And then it would switch to up, and it would stay up. Do you guys see that?
It's not actually changing the waveform.
Exactly. So the wave is basically staying in a way sort of continuous. You can sort of imagine it that way. Usually the way that we'll discuss it is the phases, right? You're going to want, right? So you want the sort of the orbitals on the same phase. Yeah, Mark.
So, the first one, this is the nucleophile, right? So what would that be called?
This would be your nucleophile in this case, because it's the highest energy with electrons. This would be your electrophile, which would be your LUMO, right? It's
The more nodes, the higher energy.
yes, right. Like a wave. Just think about like waves, right? All right. So that's one way. This would be sort of if this is the HOMO, and this is the LUMO. But as you can imagine, you could switch that, right? And let's take a look at that, right? So if we switched it, and we made this side right, now we've got that side, right? We're sort of matched the whole system there. So this side would be your HOMO, this side would be your LUMO, right? But if we look at it, right, in this case, the two nodes on the opposite sides are on the top. Right, so that's the empty one. Here, the two nodes are also on the top, so they sort of match, right? So both carbons match. Do you guys see that? A little bit difficult in the drawing. But if we can sort of simplify it, I'll use this color yellow. You're not going to see yellow on the bulletin. You guys can kind of see the yellow. Right? So on this one, see on the yellow, this is the carbon, right? This carbon's reacting with this carbon reacting with that carbon. So the node, so the sort of the sort of wave is up on the top here, the wave is on the bottom here, the wave is continuing on the top here, switching over to the bottom over there, right? And then meanwhile on this one, right? For both, it's on the same side. You guys see that? You see the symmetry in the system. So what this means, right, is what makes a Diels-Alder work is the sort of the ability of the HOMO of the diene to react and interact sort of fluidly with the LUMO of of the other. Okay, so this is what we would call, and what you'll sort of often refer to as a 4-pi plus 2-pi system. 4-pi electrons plus 2-pi electrons, okay? All right. Now here's another potential cycloaddition. It's a 2 plus 2. Mark's saying can't happen. Right? So let's take a look at it. Right? So what would be made here, right, would be a cyclobutane. Right? And the question is, yeah. That can happen? Well, let's discuss it.
Sure, there's going to be lots of ring strength.
So you're both right. It cannot happen, and I'll sort of explain, under thermal conditions it cannot happen. Under photolytic conditions, as we'll see, it can happen. So we'll explain in a minute. No, it's not a trick question. It's just, you're the one that introduced that it couldn't happen. Mike hadn't said anything. You guys are the ones to bring it up. Right, so let's, maybe it'll be easier if we show it on its side. Right, so what's going to be the reaction? It's going to be the HOMO of one with the LUMO of the other, right? So let's choose this one the HOMO. Let's make this one the LUMO. And what you can see here is that's matched, but this one's not matched. You guys see that? You guys see that? Okay, so thermally, this is not a reaction that can work, right? Because we've got one matching node, but we don't have another matching node. So 2 plus 2 is not a reaction that can happen thermally. Okay? But it turns out that there's the 4 plus 2. Okay, so here we have the HOMO of one and the LUMO of the other. And so we see, right, that this is not going to, right, this will match with this, but then this will be mismatched. So the question is, it turns out this reaction can work photochemically. Okay? And so if you were to heat this, this would work. If you shine light on this, then it will work. Okay? So the question is, how does this work? Rami?
You have electrons jumping to higher orbit.
Right, right. So Rami just said, we're going to have, if we excite this, right, one of the alkenes, not all of them, it's not going to happen all at the same time, but maybe a certain percentage of the alkenes, right, will be excited. And what that means is that you might get a jump in electrons, right? When you shine light on this, what's going to happen is you're going to jump up in electric state. So now, what's your HOMO over here? This is now it, right? That's the highest occupied molecular orbital. That becomes your new HOMO. So what's that going to react with? Your LUMO. And now we get matched systems. Okay? So what's important to recognize here is that cycloaddition chemistry, do you have your hand up? Or were you just, no? Okay, so what's important to recognize here is that cycloaddition chemistry takes way through this sort of thinking about the HOMO of one interacting with the LUMO of the other. And to sort of understand whether or not a reaction is going to proceed thermally, you have to sort of have the matching nodes. If they don't match, then usually what you'll have to do is you have to shine light on the system, and that will inevitably sort of allow the reaction to proceed. Okay? Does that make sense?
Quick question.
Yeah.
Does that have to be like a specific type of light, like UV light? Or
Yeah. Has to be a light that would allow for the excitation. So you probably have to be the specific wavelength. Don't worry about that though, just light. All right, so that's sort of the MO explanation for Diels-Alder. Okay, so draw, I guess. Okay, so in general, when you do a Diels-Alder reaction, as you might imagine, what's that? This will be on quiz 4. Yeah. Okay, so this is, quiz, So, as we sort of stated earlier, Diels-Alder reactions, we can generally think of them as being a nucleophile reacting with the electrophile, right? If this is the HOMO, it would be the nucleophile, this is the LUMO, it would be the electrophile, or you could flip-flop them, okay? But let's just start with what we normally, sort of the normal electron demand. We usually think of this as the nucleophile. Reacting with the electrophile. Oops. Okay. Now, if you were, I don't have the numbers, I have the numbers somewhere together in your book, but if you were to try to get this Diels-Alder reaction to proceed, it would probably take a lot of heat. I forget what the numbers would be. You need to go up to a couple hundred degrees, right, in order to get this reaction to proceed. And that might not be the most practical of method, especially given that these are both gases, right? But it turns out that usually when people do Diels-Alder chemistry, they're not just dealing, they have substitution on this. And that substitution can certainly change the electronics of this system, right? So let's think back to what we were talking about with sort of reactions of benzene, right? And when we put donor groups onto benzene, what was the effect? Made it a better nucleophile, right? Right? So if we added a methoxy, like we got to the point where if you had an oxygen donor group, sometimes you didn't even need those Lewis acids to promote the reaction, right? We sort of discussed this. Throw them in there just to be consistent, but that's sort of just a point, right? It's that with a nucleophilic enough, with donor groups on the benzene is a good enough nucleophile that it might just react with bromine by itself, for example, right? So what are good donor groups? Is an ester a good donor group? Ester is a good electron withdrawing group. You mean ether?
I didn't say that.
Oh. Yeah. So halogen is not it's a withdrawing group, right? Yeah. A methyl group, some sort of just a generic alkyl group, like a methyl group or something like that, that's going to be a good donor group. A methoxy group is a classic one, so oxygen donor group. So those are usually the two that we're oftentimes thinking about, right? So, so let's just, for example, put a methoxy group there, right? Okay, so that's going to make that that's going to make that diene a better nucleophile. What do you think about the other side? What if we wanted to make the alkene a better electron withdrawing group?
Carboxylic acid.
Like carboxylic acid, some type of carbonyl, basically, right? Okay. So let's put a ethyl ester on there, just for sake of having something there, right? So put an ester on there, right? That's a withdrawing group. So what are the withdrawing groups that we normally think of? Sulfonyls, for example, nitro groups, right? These are groups. Maybe even halogens. Somebody brought up halogens. Halogens might be a good electron withdrawing group. Cyano groups. So all these things that might be good electron withdrawing groups, if we put on there, that's going to make that alkene a better electrophile. Yeah.
If your dienophile has sister trans groups on it, that stereo comes.
We'll get to there. We'll get to there. Yeah, we're building to that. But the first issue is not stereochemistry, but what? Yeah. Regiochemistry, right? Because if you look at this, I could flip this over. I could have the molecule where it matches up just as I have it here. Or I could flip that upside down. So the Diels-Alder, right, is that when you have non-symmetric systems, you can in principle get a couple different regioisomers. And you guys are going to need to be able to predict which of those two regioisomers you might get. Rami.
This entire reaction is kind of just it's a Michael reaction, just a little bit tweaked.
Yeah. In many ways, yeah. It's that if you picture it this way, okay, so explain to everybody what you just meant by that.
When you have a diol, not a diol, you have a diene that's conjugated, you see that you can move the extra electron, you can move double bonds.
Well, not the diene. You just said a Michael. Michael doesn't have any
No, I
dienes.
meant the conjugated double bonds. Yes, exactly.
Right? So when we have a carbonyl, right, and what reacts with that? Right, but usually what kind of nucleophile? Or let's enolate. Let's make it an enolate for now. Right? Right, this becomes your delta minus. That's your delta positive. Right, and there's your Michael addition. Okay? So now back to over here, right? Given what we know about Michael addition chemistry, for example, let's just start with that one. Where's the delta positive? Aisha. Where my finger is, yeah, exactly, where my finger is. All right, I gave you that one. So I can be here or here, top or bottom. Which one of those two, Aisha, I'll give you a chance. Which one is where the delta, what do we want to interact with that? We want the delta negative. So which one of those sides do you think would be the delta negative? Okay, so Aisha thinks the top one. How many of you guys think the top one? Yeah, so it's going to be the top one, right? Because we can, just like we did here, right? We can push those electrons down from that double bond and put a negative charge here. We can't do that same thing over here. Okay? So if the delta minus is up here and the delta positive is down here, which one of those two are we going to get, Anna? Anna? Which one of those two? Delta minus is up here and the delta positive is down there. Which one of those two are we going to get? We want to match the delta minus and the delta positive. The second one. Right, exactly. Because we flip this upside down, this is the carbon. Right, if we think about what it eventually was, that's where the delta positive was because we flipped it upside down. That's where the delta minus is right there. Yeah, so that's going to be the regioisomer that we're going to get. Does that make sense to you guys? Okay, so this is the first thing you have to, okay, well, the first thing you have to do to know about Diels-Alder chemistry is what the Diels-Alder reaction is, right? The next thing you have to be able to do with a Diels-Alder reaction is recognize of the possibilities that you get from the standpoint of regioisomers, which regioisomer are you going to get? Okay? Yeah, Abraham.
So are these like concept questions?
No, this is the chemistry. Could be a concept question. This is a reaction. You guys got to know. This would be similar to knowing the regiochemistry of HBr across an alkene. More substituted. HBr with ROOR. Less substituted, right? So it's regioselectivity in a different case. But one of the things that makes Diels-Alder complicated, right, is, okay, so now we got the regiochemistry, you got to know that. But the one that I've shown here doesn't have much in terms of stereochemistry, but there can be stereochemistry in these as well, right? So here I haven't shown, there's only a single stereoisomer, right? So unless we did like asymmetric catalysis, which we don't talk too much about in this class, right? You can get that going forward, you can get that going backwards. Those, for all intents and purposes, according to this class, are going to be the same molecule. But what happens, now that we've established that we're going to get that regioisomer, what happens if we introduce, and we'll increase difficulty level. All right, so there's a few different ways in which we can generate stereochemistry. If we think about stereogenic centers, right, we have one stereogenic center here, right? We have the possibility for 3 other stereogenic centers to this molecule. We've got one here because it's sp3, right? So if there was substitution down here, you would get stereochemistry here. This one here would be if you had substitution there, you would have another stereogenic center there. You guys see this? Assuming that those groups are, that it's not like two groups of the same thing, right? And then up there, we'd have that group up there. So you guys see each of these carbons are sp3. And so you guys might have molecules, and you guys might be asked for Diels-Alder reaction questions, where you have substitution either here, or here, or here, right? In which case, now what we're going to have is the potential for diastereomeric possibility. So the first thing is regioisomers. You got to know the regioisomers. Second part is diastereomers. So let's start with the easiest one, I think, is if we put a methyl group down there. Okay? Now that double bond is trans, as Mark just said. That's a trans double bond. And we haven't really necessarily discussed this, but the Diels-Alder reaction is a concerted process. Sort of you would see it when we were drawing the mechanism, right? We were pushing all the electrons at the same time. So I showed it that way. It's a concerted process, right? Which means there's no possibilities in this reaction for really scrambling the stereochemistry. So the relationship between this this methyl group, and that ester are on opposite sides of that carbon. So because of the fact that they're on opposite sides of the carbon, we can draw the hydrogens maybe to help us see it a little bit better. Because they're on opposite sides of the carbon in the starting material, and it's a concerted process, what do you think that tells us about where they're going to be in the product? Exactly, they're going to be on opposite sides of the ring in the product. So it doesn't matter which one you choose, the dash and the wedge, you can flip-flop those. So I could have made this the dash and that the wedge. I just chose to make this the dash, this the wedge, and that the dash. But the point is that they're on opposite sides of the ring. So you'd have a racemic mixture right of this. So you get both enantiomers of that molecule. So that should be an easy one for you guys to see. That's a fairly easy stereochemistry. The challenging one comes when you start talking about, yeah.
Is it possible, instead of having it, like, we see it kind of, in this case, we see it kind of adding in sideways. If we actually just kept it as it is, we had them both planes of the board. You have a methyl group going into the ring. Is that possible?
Into the ring, no, because then you're going to break. I don't know, I'm not quite seeing what you're saying, but what it sounds like you're saying is you're distorting the stereochemistry beyond the, the normal 109-ish, right? So, all right, so, okay, so we'll get back to this in a second. I'm going to actually, to introduce the new type of stereochemistry, I'm going to take a step back and actually show you an alternative Diels-Alder that I think makes it a little bit easier to address this next component of stereochemistry, and then I'll return to a system like this. Here's cyclobutadiene. What do we know about cyclobutadiene? It's got a lot of ring strain. What else do we know about it? It's unstable. Why? Not just because of ring strain. Come on, we just spent a week on this. No. What's that? It's anti-aromatic. Right. So it's anti-aromatic. Right. It's a cyclic system. It's got a complete series of p orbitals in a row. It's anti-aromatic. You cannot isolate this molecule. If you isolate that molecule, it will rapidly react with itself through, guess what? A Diels-Alder. What's that? It's like a little silverfish. Right? Do you guys see that? It's a little bit challenging to potentially see, but I'll just draw it that way for starters. What's that? Show both of what? There's the 6-member ring, there's the 6-member ring, and then the middle sorry, there's the 4-member ring, there's a 4-member ring, and then they're making a 4-member ring in the middle. So the cycle addition, we're making 2 carbon-carbon bonds. You guys see that? Okay, now what's,
Does that actually exist? This product? Does that
oh
exist?
yeah, this is known. This reacts and makes this.
That one, assuming that also has a large amount of
Oh yeah. Okay, but what's interesting about this is what I'd like to ask you guys is think about the stereochemistry of that product and tell me how many different stereoisomers you might generate.
There's a lot.
A lot of stereoisomers? That'll be the first question for you guys today. How many stereoisomers of that molecule? That would have been a good exam question, right? How many stereoisomers of this molecule exist? Yeah. So I've got to vote for 4. Got to vote for 2. What's that? All right, so let's start with the 4. I'm going to tell you right now, 2 and 4 are the best answers. 2 is right. 4, and I'll explain why in a second. 4, yeah, what you were. So 2 of the molecules are the same, right? You were probably saying one face, the other face, right, and the other or. But it turns out that if you move them around, you see that they were identical. So yeah, so it can lead to 2, right? And we can describe those 2. Again, these protons are on the same side. They're going to end on the same side. These protons are on basically the same side of that. They're going to end up on the same side as well, right? So, but the relative relationship between those can be different. Are you guys familiar? So we don't show it that much, but you guys familiar with the big, like, circle, dark circle? That's a proton coming towards you. We show it every once in a while, right? So that's a proton coming towards you. That's a proton coming towards you. Okay, so either all the protons can be on the same side, or 2 can be on one side, and the other 2 can be on the other side. And if we were to draw these in 3 dimensions, right, that would be one of them. It would kind of look like a C, the shape of a C, right, where all the protons are on the same side. You guys see that? Right, that one bond is going behind that bond there. And the other one would look more like an S. Right, where the protons are on the opposite sides of one another. You guys see that? So see how on the left one, all the protons are on one face. On this side, all the protons, the 2 on the top are on one side, the 2 on the other side are on the other side. You guys see that? Okay, so these are the 2 possible cycle additions that you can get. These have names. Go back to this one. This one, where the 2 groups are on the same side, are referred to as endo. And these 2 that are on the opposite side are what we would consider exo. Okay? Now, if I were to give you these 2 possibilities, and show them to you, and I was to tell you that this is a highly selective reaction only led to one of these 2 stereoisomers, which one would you guess? I've got 1 vote for endo. I've got a vote for exo. What would you guys think? So, how many people think exo? How many people think endo? So, more hands for exo than endo, and the people that said endo probably have read ahead. Because I would expect that you guys would say exo, right? You look at the structure of the exo, and somebody said exo. Tell me why you thought exo. Strain? Well, that's not strain. That would be something else. Hindrance, sterics, right? You're bringing the 2 groups close to each other, so sterics. And that's the answer that I would have looked for, right? Would have been this. That would have been higher in energy because the 2 groups are kind of close to one another, and that would be bad. right? And that would be what I would expect you guys to guess, because guess which one of these two is probably the thermodynamically favorable product? The second one is the thermodynamically favorable one. But as Mark said, and some others that raised their hands, this is actually a reaction that goes endo. So this is a weird scenario here where the product, you would expect that the product would actually go to the exo, because that would be the thermodynamically favored one, except that Diels-Alder chemistry will very, very, very often go endo. And this is something called the endo rule. Okay? And the endo rule has to do with, if the one is thermodynamic and yet it's not going to the thermodynamic, then it's going to be the kinetic product. And the question becomes, why would the transition state to the endo product be favored? Yeah? Nope, it's not going to react again. What, you were thinking like a 2 + 2 at that point to make some crazy cage structure. I don't usually, this isn't really in your book, but yeah. It's not in your book. I'll just, yeah.
I could think, yes, you have those two double bonds. Is it possible that since those are kind of, I mean, again, they're not really because they're not actually bound to each other. You have some kind of conjugated type of thing.
I think you're kind of getting there, Rami, a bit. It's what we would call the sort of reason behind endo selectivity, sort of debated for a while. Recent papers have come out that have pretty much confirmed, or the current thinking is that it has to do with secondary orbital interactions. Okay? And what I mean by that is, right, if we draw this reacting, right, and we think about what's happening here, right, we'll make this one there will be our diene, right? There will be our alkene, right? And so the orbitals that are interacting, right, are that blue one, right, with the yellow one. So the blue orbital that I showed is interacting with the yellow orbital, and that's how we're sort of making the bond here, right? Maybe I should have kept it that way, but let me just show you guys something so you realize, you can kind of see what's happening here. Because it's facing the opposite way. Green arrows are going to go there, to there, and then back up to there, right? And so that's what's going to ultimately make those two bonds there. Do you guys see that? Okay. All right. So if the blue and the yellow are where the orbitals taking place, I talked about the secondary orbital interactions. What do you think the secondary orbitals are? This pi bond and this pi bond. Okay? In a transition state where these are coming close together, what do you think can happen? You can have an additional pi-pi stacking interaction between those two, and that turns out as a favorable energetic process, sort of secondary orbital interactions, that happens to lower the transition states enough that the reaction will favor endo-selectivity, kinetically. If it's a kinetic reaction, yeah, Ron.
If we saw them as the HOMO and LUMO, it would be easy to see, because you'd see that
well, that's what I did. Well, I didn't really choose which one was HOMO and LUMO here, but I can. We can make this one the HOMO. and that would be the LUMO.
No, I'm saying for the second. Oh, yeah, sorry.
Or actually, flip-flop. Maybe I'll switch these up. So this is interacting there. So we have mesh nodes there. Yeah.
So because those middle bonds are all single bonds, why can't they just twist back into that S shape? Why do they
Well, you
stay-
can't. You have to break. You have to break that. You can't twist
can't
it.
just go like,
No, no way. No. If you try to flip this over, those protons would end up like being in the middle of that ring. You can't just flip over the top. You'd have to break the. You'd have to eventually go through a planar transition state to do that. Right? Imagine if this started going up in this direction.
yeah.
Once it got here, right?
Why can't those just
Look
go?
at the
Yeah, I guess the best answer I can give you is try to build a model and just try to do what you're trying to describe. You'd have to. It's gonna break apart. Yeah, it's gonna snap apart because these protons. It's not like these protons can just jump through. Right? So as you're going up and up and up and up and up, this proton's going to come close to this carbon, and you're never going to be able to go past that. You know, you're never going to be able to go past that. So you cannot interconvert between two stereoisomers through just rotations, generally, in most cases. Okay, so that's pretty tough to look at, right? It gets harder. And I think this is one of the easier ones to see it on, is cyclic glutathione. It gets a lot harder when we start to get to normal system, like what we had earlier. So previously we had something like this. I don't know, it wasn't exactly this, but let's switch where that methoxy group is, right? The methoxy group's on the top now. Okay. Quick revisiting. I got two regioisomers. Let's just have a pop quiz, not really a quiz, but let's just try to get you guys thinking. There's two regioisomers here. What do you guys think the regioisomer is? Don't say it, think about which one it is. It can be one way, it could be the other way. We already know the delta positive is where. We treat this as the electrophile. Where's the delta minus of this?
There.
Where?
The one that. No, the one. Yeah. Right there.
Okay. And what's that? And what's that? So we're already lined up the way that we go. Remember that these delta positives, delta minuses go away. Right? Okay, so in this case, what we're generating is a molecule, and I'll show the stereochemistry in one. We have a new stereocenter there, right? And it turns out that what that stereochemistry is, whether it's going towards you or whether it's going away from you, is going to be based largely upon endo or exo selectivity. Okay? So what we will do is, what's that? Not a chair. We don't do chairs in these cases. It's more like what we showed earlier in terms of the square. We're going to see chairs a bit when we get to other classes of pericyclic reactions, but yeah.
What happened to the original oxygen?
What's that?
The original oxygen.
I just got rid of it. I moved it. I just moved it over here. Oh, sorry. Yes, my bad. Thank you. Yeah, I had a typo. Yeah, so the oxygen, so that, sorry, that OME, came that OME.
Thank you.
Yep. Okay, so the question becomes, what's the stereochemistry of that? And if this is an endoselective process, how do we sort of determine whether the product is endo or is the product exo? And let me just show them both. So again, we're not going to worry about just racemic, right? Not going to worry about asymmetric processes. One of these is going to be endo, one of them is going to be exo. And the question is, which one is which? You've got to vote for second one being endo. You've got to vote for first one being endo. The answer is we've got to draw it to be able to see. Okay? And the question becomes, how do we sort of visualize this? And what I think is helpful, what you're going to say, Ron?
Could you draw, wedges or dashes within the ring itself to show?
Well, I think what I would do is I would basically do that same square that we did before, right? If we draw the square, and we can even draw the square because right, some of you guys are used to drawing squares, right? What we can do is we can sort of draw this square as our template, right? You guys draw squares, 3 dimensions. Draw a square. This is something that I think you learn in 5th grade, right? So revisit Billy Madison, okay? And then, yeah, it's not the best square, but it's okay. And then what we're going to do is we can basically map the molecule on top of it, right? So let's make this one blue. And here we have the OME. And which direction is the OME going, as is drawn? It's going out of the board. Wait.
Wait, which one? Which one we did?
This one. When I drew this way, and I tilted it that way, I've got a proton and I've got an OME. It's going that way, yeah. Huh? The cube? Right, so the methoxy is going to be going back, and sometimes it's helpful you can even draw the proton going towards you. Okay? So, and you look at this, right, and this is kind of this is the trans double bond, right? There's your trans double bond, right? All right, so we can get rid of this guy in the middle, or just draw. All right, so what's going to be on the bottom? Now we can draw the alkene on the bottom. This is where we're going to be making the bond. Now, the challenge here is we can basically, this carbon here, is going to be this carbon here. Right? And so that carbon is going to have a proton and it's going to have an ester. If this is endo-selective, which way is the ester going? Well, okay, let me rephrase that. Is it the left one or the right one? Which one's the ester going to be? If this is endo-selective. The left one, it's going to be the lefto if it's endo. Irina, because endo is basically the group that has the p orbitals is pointing in this direction, is pointing towards the tail end, just like what we saw previously, right? And if we draw it out, right? If you think about that, it's because this p orbital here. You see that? So those p orbitals, as you can imagine, are now going to interact with one another, right? Which means the proton is now coming this way. Okay? All right. Brain hurts yet? Okay. All right, stick with me. Stay with me here. Okay. So now what we want to do, now that we've set this reaction up, right? Now, right, we recognize that the ester is coming this way, the proton's going to be going that way. And what we need to do is now we actually want to get rid of everything else that's not really involved in this reaction, which I had done up here. Right, and that's ultimately the Diels-Alder that we're doing here, right? We're going to make that bond and that bond, okay? Which means What's that?
It's a boat, right?
As is, it's a boat. Now, what we want to do is we want to sort of, in a way, open this up. And now I'm realizing that I didn't draw either of these. I drew the enantiomer of them. Just turned out that way. But that's okay. We'll just move forward with it. What we want to do is we want to open this guy up a bit, right? And if I were to open this guy up, right, and if I were to open this up, if I were looking down this way, right, what am I going to hit first, the proton or the OME? If this is opened up, if I open this up to make it a 6-numbered ring, which is going to be first, Irene? If I open this up, that OME is already going back, right? Right. So we're going to see the hydrogen first. You guys see that? So if I were to open this up, imagine that bending that way. The proton's going towards you guys. The methoxy's going back. If I open it up, right, the proton's going to stay going forward. The OME is going to be going back. And we'll show potentially some other ways to see this as well, right? And again, I'm still looking from this way, right? What am I going to hit first, the proton or the ester? Proton, right? Okay, so I didn't draw exactly that molecule. I drew the enantiomer of it, but which one is it? And that was the first one. Yeah, go ahead.
So two possible outcomes of the world are always going to be
Well, this, so that's why I said it's racemic. So this is the enantiomer of this. Huh? So you see how it's the enantiomer? Right? Because both these are going forward, both these are going backwards. So these are enantiomers. You guys should at this point be able to pick that up. Right? If they were, if this was towards and that one was back, that would be the enantiomer of that. So there are 4 possibilities. I happen to draw the one that went to the wrong enantiomer, but we're not asking about specific enantiomers. So this and that are the same. Okay? You know, another way that you can sort of see this, potentially from the transition state, it might be a little bit easier. Again, this is something that I go through it, and I'm sure that I'm getting a lot of glazed eyes right now because I get that this is one that's, I think, difficult to process and it's difficult to see. And you guys have to sort of struggle with it a little bit, try it on your own, maybe build models to see. But there's other ways that you can sort of take a look at the relationship between these molecules, right? If you look at this structure right here, right, the ester, right, and the proton, right, if you think about it, this proton is closer to that proton. Right, and this ester is sort of closer to that OME. If you think about these going back in that direction, right, and we're coming from this direction, right, these protons are going to be on the same side. That ester and that OME are kind of going to be on the same side. So as you look at this a little bit closer, you know, and you struggle with it and you sort of look at it, you'll hopefully be able to sort of see this a little bit more. Okay, so this would be endo. Okay, so this is endo. If the ester was on the other side, you get the exo product. Okay. All right. So let's try one.
Yes. Let's do it.
All right, so so here's the Diels-Oliver reaction. You don't even have to worry about regioselectivity because I made it symmetric. Actually, no, forget it. All right, no. All right, so here's a Diels-Oliver reaction. You guys got to get to the product, okay? And the first thing that you guys have to recognize, and the first mistake that students will often make, right? I just want to sort of put this up here for a point, but I'll go through it with you guys because we didn't bring this up. Is a question that came up earlier about the S-cis, students will very commonly make a mistake when they start to convert the linear to the S-cis. Remember, for the Diels-Alder, we need to draw it this way, right? And we still have a methyl group here. So that methyl group could be here or there. And it's very common for students to make mistakes when they put that methyl group on the S-cis conformation. So the methyl group on the top is going down. Rami says it's going down. Do you guys want to believe Rami? And the way that you can sort of see this, he's right. He's right that it's down. Where students will struggle sometimes with this is they'll, I guess, be lazy, I guess. Just, I don't want to call it lazy, but they'll just, they'll see the methyl group going up, and they'll just leave the methyl group going up. Rami, how did you know that it was going down?
Well, because I kind of just left the one with the methyl as is, and I just flipped the other one, so I saw kind of.
Well, it's not just that. I mean, what's the stereochemistry of that alkene? Cis. So it's got to stay cis, exactly. You guys see that? So you got to make sure that if one of the alkenes is cis, you got to keep it cis. If it's trans, you got to keep it trans once you try to rotate to that sort of S-cis. Okay, so first question now is we got to draw the Diels-Alder reaction. And before worrying about stereochemistry, we have to worry about what? Regiochemistry, right? So the first question you guys have to do is identify the delta positive, identify the delta negative, and try to figure out which way it's going to react. Is this going to react with this in this fashion? Is this going to react with it in that fashion? So at this point, we're probably pretty capable of figuring out where, because we've been seeing this over and over again, where's the delta positive in this system? On the bottom, or over here on the top, right? So it's going to be at the beta carbon of the ester. Right? That's one that we get pretty comfortable with. How about the guy on the left-hand side? Which one of these is delta minus? I've got one vote for the top. A little bit more difficult because we don't have enolate in there, but we just have to think about, you know, one of the things that you guys can sort of think about is I got to vote for the bottom being the delta minus. Maybe I should have answered that just in case it was like something important. So which one is the delta positive? Which one is the delta negative? Yeah.
I think it's the top because the methyl is a donor group, so it makes it more negative.
Let's ask this another way. So okay, so here's our options.
It's the one on top because you have the conjugation.
So we could potentially put the negative charge there. Right? What about down here? What's the resonance form from there? You have to think about the conjugation here.
This goes back to the way it was.
We could put that negative charge over here. Likewise, we could put the positive charge over there.
Well, the positive charge is not going to go to primary.
Bingo. Right? So one of them you put, it's not this one. I mean, these are both secondary carbocations. Does everybody see that? So this in and of itself, the first resonance form isn't quite enough. You have to go to that second resonance form. And what you realize is when you draw the second resonance form, that's where they actually distinguish themselves from one another. Right? This versus right? So this is ultimately where they distinguish themselves. So that can be a little bit more challenging, but it's actually no different. If you did it on the methoxy, it would be the same thing. But I think part of the thing is you guys have gotten comfortable seeing enolates, so you're quick to recognizing it. But if you think about the methyl group is kind of like that. If that methyl group was an oxygen, right, you could draw the enolate and you would sort of recognize it. So you could also just do a mental switcheroo of the methyl group for the ether if it helps you see it a little bit better, just making sure you don't actually literally change that. But if you sort of consider that whether it's a methoxy or whether it's a methyl group, they're going to be the same. And which you guys have seen already, right? You saw this with the aromatic substitution in terms of regioselectivity, right? The methoxy or the methyl group, they both directed in the same place. So the methyl group is substituted for that, okay? All right, so we're going to go with this one. Okay, so that's the first step. So what I need you guys to do is I need you to draw the product. Let's not worry about stereochemistry yet. Let's just focus on the bond connectivity here. Right? So when you guys get a question like this on your quiz, it'll probably be a series of, do you have a Diels-Alder product? Let's say, for example, I don't know what the points are, but let's say a 6-point question, right? Do you have a Diels-Alder product? 2 points. Is it the right actual regiochemistry? 4 points. Is it the right stereochemistry? The full 6 points, or something like that. So the first thing is you gotta make sure you get, well, I guess the first thing is you have to make sure you actually know what the Diels-Alder is. That might be good for a little bit. The next thing you have to do is you need to make sure that you get the right regioisomer, right? And we just did the first few steps. This one's gonna react with this one. Right? So the product of this is going to be what? It's going to be a 6-membered ring. Right? Is it 6-membered or 5-membered? It's a 5-membered. All right. Where is our?
I know the methyl's on the wedge.
Where's the methyl group? Here, here, here. Right? What's here? What do you mean by nothing? I don't have enough carbons here. What's there? This carbon, right? This carbon is this carbon. Right? That 5-member ring is that 5-member ring. Right? And what's at this carbon? And this carbon is hydrogens.
Are you able to draw a double bond on wedge or dash? That's what we can do.
Well, we'll get double. Wait, huh? Well, if we're drawing the double bond on its side, yeah, you can. All right, which means the methyl group is here, right? Okay. All right, so that's now you're at 2/3 credit for the question, right? So you got the right regioisomer. The next step is you got to get the right stereoisomer, and this is the hard part. This is the super hard part, which I get, right? And so what we have to sort of ask ourselves here is, ordinarily, you guys should assume, for the most part, the Diels-Alder chemistry is going to proceed to the endoselectivity. So if I ask you to draw a Diels-Alder reaction, usually what we'll be looking for is endoselective. Yeah.
The methyl's on wedge. I'm 95% sure of that.
The methyl group, well, you have to start somewhere with something.
Right.
Right? So if the methyl's a wedge, then the question becomes, are these guys dashes or wedges? And that's, one of them is endo and one of them would be exo. One of them would be exo and one of them would be endo.
Those are also wedges. Hydrogens are also wedges.
So you think the hydrogens are also wedges? You got a 50 shot, unless you're thinking through it, you got a 50-50 shot. How did you think through it? How do we do this? Again, we have to actually look at the structure, right? So, hold on, because we got,
Because we want to see if
are we out of time? I think we're out of time. Which way am I going with this? Going this way, right? What's on the same side, the methyl group and the proton?
both wedges.
You're right.
You see also, if you want to try to bend it, like use that center bond as like the spine of the book. The only way it can actually be bent in the proper way is that it goes on wedges.
But that's another way, if you guys draw it this way, you can sort of see that the methyl group and the proton are on the sort of the same side, right? If that goes that way, that's going to be on that side. So in the endo, the methyl and the proton. Okay? All right. That's Diels-Alder. Wednesday, we're going to be doing Cope and Claisen, which is another challenging one. So this is a challenging week. So hit the books.